But I'm going to show it to you in the most dramatic way, okay? By showing you the future of our own galaxy, the Milky Way. As we know, it's on a collision course with Andromeda, our nearest neighbor. So you can ask, let's look in the future, okay, billion years into the future. We're on a collision course with our friendly galaxy nearby, and here's what happens, okay? So here's a movie, a simulation of what's going to happen with the Milky Way and Andromeda. And you see they're on a collision course, but notice what's going to happen. They come together, they start sloshing together as this happens, and eventually come back together, slosh again, and eventually they relax into a single galaxy, okay? This is our fate, okay? And remarkably, we'll survive this. This is our future. Now, notice that this was a very interesting movie. In fact, let's imagine this for a moment. If Andromeda and the Milky Way were just 2 points, right, and they came together by gravity, one thing that could very well happen is they would just slingshot past each other, right? There's no reason why they should merge to something together. Whereas in the movie, what you saw is they come together, they want a slingshot, but they kind of like slosh around and they come together. It's as if there was some friction that's kind of sloshing them and bringing them together. Does that make sense? If they were 2 particles, you would expect them, okay, there's no reason why they would actually, they might form a bound state, they might start, but why would they merge together at the center? That usually think of friction. That's a very interesting process, okay? And it has to do with the fact, of course, that they're not particles. They're made up of a whole bunch of particles. You have to think about a lump of particles coming together with another lump. What happens then? It's not 2 particles, it's a bunch of particles together. It's a process known, a very well-known process dynamically, known as dynamical friction. It goes back to Chandrasekhar. So dynamical friction, it's a form of, there's no friction fundamentally, it's just gravity, but it's a form of effective friction that comes about from the fact that there are many dark matter particles around in these galaxies. Let me illustrate to you. It's a very simple process. So imagine at the top, imagine you have a mass m, which is passing through a gas of other particles. This mass m could be itself a particle, okay? But let's just imagine, to illustrate it, it's a particular body that's moving through this gas of particles. At the first instance, of course, it attracts gravitationally the particles around it. Then it moves away, but those particles then moved in because they were attracted to that body initially. That's what you see in the second plot. You see there's a little bit more particles on the right in the second slide, and that's because the object attracted those particles in. But as a result now, there's more dense particle, there's more mass, if you want, on the right, on the right than on the left, you see? So as a result, there's a force now, a net force, bringing the mass back to where it came from. Does that make sense? Let's think about it again. So you start with the top. This particle is moving around. At the first instance, it attracts the particles around it. Particles come in, now the mass has moved, but now there's an overdensity of particles. That attracts it back, right? Which means it slows it down. And so on and so forth. Now, in the second slide, it attracts also neighbors, brings them down, attracts them back, okay? So this process is precisely the process which slows things down and it's what leads to the merger, eventually. We call this dynamical friction. Notice that it critically hinges on dark matter particles being individual entities, being able to move around, rearrange themselves independently. So you see they come about, and now as they come about, now the sloshing is beginning, and that's again the dynamical friction. And it leads at the end of the day to the merger. Okay, what happens with the superfluid? The hallmark of a superfluid is that it has no viscosity. What's viscosity? Viscosity is the resistance of a fluid to flow. You notice, you say, honey is more viscous than water because it's harder to pour it out of the bottle. That's because it resists to the flow. In fact, if you think about it, and maybe you've had that experience, imagine you took your bottle of honey and you punched a little hole with a needle at the top of your honey bottle. You turn it upside down, and you know what happens? Nothing will flow if the hole is too small. And that's because of viscosity, you see? Water would come out because it's less viscous, but honey will just stick there, okay? Notice what's going to happen with the liquid helium. I'm about to show you a movie. Here's again our favorite bucket of liquid helium. Initially, it's not going to be superfluid. At the bottom of this bucket, they did exactly what I said. They punctured a bunch of tiny little holes. Just like honey, when it's normal liquid helium, nothing's going to flow. But when it reaches critical temperature and becomes superfluid, you'll see stuff starts to pour through the holes, even though they're extremely tiny holes. Okay? Let's watch the movie. Initially, it bubbles, nothing goes in, becomes superfluid, and now you see at the bottom, you see stuff pouring out. Right? Let's see it again. You see, initially, nothing comes out, cool it down, stuff starts pouring out. And that's the hallmark of superfluid, the lack of the zero viscosity. It can flow through anything, no matter how small the capillary, no matter how small the tube, it will flow through it. Okay? That's a superfluid. Now, what it means in practice, of course, I should qualify this. It's no viscosity at absolute zero temperature. If you're at a little bit non-zero temperature but below critical temperature, there will be a little bit of viscosity, okay, in the fluid. But in any case, what we expect for us, if you think about the dark matter fluid, superfluid, is when you had these galaxy mergers, you expect there will be less dynamical friction, less viscosity between the galaxies as they're moving together. So it will change a little bit how galaxies merge, you see? It will change. They'll still merge, right, because these things are not at absolute zero temperature and so forth, but it will be less dramatic than what you saw with Andromeda and the Milky Way. Less dynamic. Now, why is that a good thing? This is pretty subtle, but let me give you some, you guys are jury members. You want to know evidence for this crazy idea. So what are the evidence that leads me to think that less dynamical friction is a good thing? Less friction in the dark matter is a good thing. Here's one of the dwarf galaxies, satellite galaxies around the Milky Way. It's known as Fornax. Now, here it is. As you can see, it's a very feeble galaxy, has very few stars compared to the Milky Way. And around it, I've circled some points, okay? These are clusters of stars. We call them globular clusters. They're in orbit around Fornax. Now, if you believe ordinary dark matter, these little clumps of stars in Fornax are swimming in the dark matter halo. You see? They're swimming in the dark. Dynamical friction, just based on the little animation we saw earlier, dynamical friction should have led these clumps of stars to go towards the middle, towards the center of Fornax, precisely for the same reason that our galaxies merged. And they don't. They just happily stay where they are. They're not moving to the center. Somehow they're prevented. They're orbiting, but their dynamical friction is not bringing them to the center. Now, conventionally, you could interpret this as maybe the dark matter halo doesn't extend as far, or so, maybe the dark matter distribution is different than we think it is. But in my case, this is explained quite naturally. These clumps of stars are swimming in the superfluid. They're not feeling the viscosity. They're not feeling the dynamical friction that would bring them to the center. That's how I explain why these guys are staying where they are as opposed to being dragged to the center. Here's a galaxy cluster. And remember, I told you galaxy clusters don't have a superfluid except near the center. Okay? Here's a galaxy cluster. What you see near the center, you see this bright yellow region. That's the brightest region of the cluster, and it encloses the brightest galaxy in the cluster. But notice, if you squint your eyes, you actually see 3 little dots within the yellow region. You see that? Those are actually 3 galaxies. They're so close to each other that if you believe they have this dark matter halo around them, their dark matter halo are basically overlapping. So now you can ask, wait a minute, you showed me a movie of 2 galaxies merging, and when their halos were sort of overlapping, they merged. Why these guys near the center of the cluster haven't merged? In principle, their halos are overlapping. That's very interesting. It's a puzzle. People, you can come up with. But again, in my case, this is explained. Yes, they have halos of superfluid, but they're superfluid. So the merger is very different. They don't feel the same kind of friction that ordinary dark matter would give them. Okay? Anyways, hallucinations. Hallucinations from a crazy theorist. Now, some other very interesting observational properties of superfluids is when actually superfluids collide, what actually happens. So people do that in the laboratory. So here's what happens. You take 2 lumps of superfluid, bring them together, okay? You see, eventually, they come out, and notice that they came out, and they retain their shape that they had initially, right? So this is, again, a hallmark of the fact that superfluids pass through each other without any dissipation without any friction. They're happily passing through each other. But what did you see in the middle when they were overlapping? You saw fringes. You saw these lines, right? Let's look again at this movie. You see they come together, and when they're overlapping, you see what we call interference. You see dark spots and bright spots. And that really is due to the quantum mechanical nature of these guys. It's the fact that they're quantum mechanical that you see these interference, much like we see with the two-slit experiment as one of the evidences for quantum mechanics. So when people simulate, so people have done simulation not of my superfluid, but a related type of dark matter superfluid. This is again like the blue movie I showed you earlier with formation of galaxies. I'll show it again in a second, but you see again these lumps forming. These are like the galaxies eventually. You see them coming together, and you see the wiggles, no? You see them, the ripples around them? Those ripples are the same interference effects that we saw with the experimental lumps coming together. Okay, let's see this again. So you see they come together. They form, first you form the lumps, you form the homes that will later be galaxies, and then they start coming together because of gravity. And as they come together, they form these fringes, okay? Could you see this? Well, there is actually there are known structures around elliptical galaxies. There are these beautiful rings. They have, truth be told, a conventional explanation within standard dark matter. But this kind of interference that we're discussing between superfluid could have another contribution to these kind of shell-like structures that we see around elliptical galaxies. Perfect. So I want to leave you with some thoughts. I told you, I brought you on a journey. The first thing that I want you to take home is that dark matter as a particle is highly successful. It's most successful in the DNA piece of the evidence. It's successful on the largest scales in explaining the cosmic microwave background properties, the cosmic web, gravitational lensing. So all the large-scale stuff works exquisitely well. Meanwhile, this Mon empirical law works beautifully with galaxies. Doesn't work well on the large scales, but on galaxies it works amazingly well. You should think of it not as a theory, but as an empirical fact about galaxies. So is there a way to marry these two ideas together without giving up altogether the idea of dark matter, still keeping the successes of the dark matter, but then incorporating this Mon behavior not as a miracle of star formation and so forth, but as a real fundamental property of dark matter? And the idea that I presented to you is something that I've been working on actively, is the idea of a dark matter superfluid state. As I told you, it's not crazy in the sense that we know with cold atoms, you cool them, you make them dense enough, they form superfluid. So if dark matter is of that type, there's enough dark matter and it's cool enough, you will form a superfluid state of dark matter. And in this picture, really dark matter as a particle and as a Mon phenomenon, it's really two sides of the same coin. They're just different phases of the same substance. It leads, I think, to eventually a rich spectrum of predictions, in particular for these mergers of galaxies, as we saw. Dynamics should be quite interesting. And I want to leave you with some open questions that I think are fascinating and that I'm thinking about actively. What would be a precise analog? I told you it looks like cold atoms that people study in the laboratory. I told you mathematically it looks similar to the theory that describes those cold atoms. So can we find an actual cold atom in the laboratory whose properties would be identical to the kind of superfluid I need for a Mon? Okay? Does that make sense? If you can find such a actual superfluid in the lab, you could, in principle, within the laboratory, start simulating galaxy collisions with cold atoms. Okay? That's the ultimate dream. Can you find such an analog in the laboratory that would allow you to study galaxy mergers and so forth? And of course, the elephant in the room is dark energy, right? I didn't discuss dark energy, but dark energy, which makes up 3/4 of the energy budget of the universe, is itself a big mystery. What is dark energy? Ideally, it would be very nice, if dark energy could somehow fit nicely, holistically in this picture. Maybe not in this particular superfluid picture, but in general, as some other phase of the dark sector, not as opposed to just another ad hoc component we add to the budget of the universe. Thank you very much.